So, okay, standard random graphs. So we've figured out for these things, right, which is almost all of the networks in here, but none of them in the real world, that we have this kind of nice connection, right? So if you choose a random node or you travel along a random edge, then the number of other friends that node has or the number of friends your randomly chosen node, they're the same. And that generalizes out to the component sizes as well. So we just have one equation. We're going to set this. We can rearrange this whole thing. Right, so this is just the first derivative. And we'd set x equal to 1 here, 1 here, 1 here. Which is not bad. And we can simplify things, that's true, right? So the first derivative of the p-generating function is, this is a result we had, right? So it's the average degree times this one. Yep. For, yep. This is for standard random graphs, right? Okay. So you don't have to worry too much about the details, but this is just for things with Poisson degree distributions. Yeah, this is painful. So we can replace the top part as well, because we already have this equation. We're going to set x equal to 1. And then we replace this is the sort of fundamental thing, is that the probability that a randomly chosen node is part of a finite component, which is what this is 1 minus the probability or the fractional size of the giant component. Okay, so end result is going to be this. And so we got to this before, it's a while back, but we got to this before. The average component size for Poisson degree distribution networks looks like this. So this is the fractional size of the giant component, and this is the average degree. So we're going to tune this thing. It's going to change the fractional size, right? There's a phase transition. So for low average degree, this is 0, 0. And then as we tune it up, eventually this becomes non-zero, and this starts to sort of depart in a different way. So what's going to happen is that the average size has to go to 0, because it's the average size of a finite component. Eventually, when this is, right, when this goes to infinity, bless you, when this goes to infinity, this is also going to 1, so these things are balancing each other out. But it must work in such a way that this goes to 0. All right. Okay. Yeah. So maybe just the thing to show here, we found that the average degree equals 1 is the critical value for the system. Right, that's when you start to get a giant component. And, all right, this is what it is. For all average degree less than 1, then we have that the giant component size is 0, so all of that collapses just to this. So this is the average component size. It's actually the complete average component size, right? Everything's finite below an average degree of 1. So you can see what happens. So when average degree is 0, everyone has no friends, right? So we just have 1. And as the average degree goes to 1, this is a very important thing of critical systems, not just this thing, but in general, it's a very fundamental thing. This goes boom, right? This explodes. So in stat mech, this is often kind of the approach you use to find a giant or a phase transition. Like something is going to go pop. And it's kind of easier to find the things that go, bonkers, right? So that's what's happening, right? This is going to, and as we actually get to that, right to that limit, we actually have a parallel size distribution of component sizes, right? You've got a really big one, but you've got them of all scales, and then boom, suddenly you've just got one big one and all these little characters. All right, so this is a very nice result. And I really don't have a, these are some notes from before. Yeah, let me use these. Right, so this is the kind of thing you see. This is the fractional size of the giant component, right? It's 0, gets to an average degree of 1, takes off. So we've seen that one before. And this is what's happening for the average finite component size. it starts at 1, explodes, right? So when you look at this network right here, there really isn't, right? The biggest one is still size 0. It's actually kind of it scales with the system, n to the power of something. But the average size has exploded. And then as you go past this and you start to have a giant component, now you're just looking at all these ones around the little ones, right? So you've got this giant component, and now you're just looking at the average size of all these little finite ones, and that's going to decay. Because eventually everything's in the giant component, and these ones out here will have, if you're not part of this thing, you basically have no friends, you're out here. It's still possible to have someone with no friends, even as the limit goes up and up and up. Exciting? Exciting. So a little bit of struggle to get there, but we get a very important kind of result for a lot of these systems, is this critical, and this is where critical points come from, right? There's something, the thing can explode, right? If this is something that, is governing some other system, you're measuring, right? Your headphones are dialed to this thing, right? This is the volume, kaboosh, right? So it's kind of bad. So that's where we get this framing of critical points. That's reasonable. Okay. These are the other limits, right? So so we've got this as it goes to infinity. As I said before, the average size goes to 1, and the average eventually it has to go to 0, right? There'll be, that's interesting. I should think about that a little more. Because if there's any one by themselves, then they'll have one friend. Okay, maybe it's 1. Yeah. All right, doesn't matter too much. Okay, so and these are results. So because there's a lot more pain involved potentially. But at average degree 1, if we have a finite system and we look at its scaling, then this is the size of the giant component, right? So it's growing as n to the 2/3, and then this is a fractional size, so we'll divide by n. But that's really the big thing, right? So it's considerable, but it's rolling over. That it's a sublinear power. That's only at that point, and for less than that, then we have the typically largest one is growing like log n, which isn't fast. I guess there's some prefactor there. All right.